Hi, welcome to the OpenACC workshop presented by the NSF XSEDE program. This was originally a one-day hands-on event that you can view at your own pace. If you look at the link below, you can get access to the content and slides used by the original students.
What we're going to do is we're going to look at the kind of the 50,000-foot view of parallel computing so that when we talk about OpenACC today and what it can do and what it can't do and where it's applicable and where alternatives should be used, it'll make some kind of sense. And I think that that's really important. Otherwise, it's too easy with the different components that make up computing today to not understand where things apply and don't apply. Well, I'll make more sense by the end of this talk. So, first of all, I hope that many of you are bringing applications in mind to this workshop and have some motivation for why you need to use GPUs. Some of you may not, and it's just you're preparing for the future knowing that GPU computing is an important part of being able to do any kind of numerical work. This stuff is now on, again, every laptop, every workstation, if you're running CAD programs, things like that. But the driver for this stuff is actually a very large supercomputing-based community that's typically doing things where no matter how much computing power they have, they always want more. A good example of this is looking at climate change analysis, for example. You're trying to do what is essentially fluid dynamics problem. You're trying to understand how the atmosphere and its components interact also with the ocean. And you're trying to do what looks like weather forecasting. And weather forecasting in and of itself is a very challenging problem, one that has achieved great success over the past couple of decades, primarily due to parallel computing. But you're trying to do weather forecasting over scales of decades and over not just your state or your region of the country, but the entire globe. And so it's a good example of a problem that the bounds of it are obviously enormous. The computing requirements are obviously huge. And we can see with this problem in particular, we can see how great progress has been made with parallel computing, with heterogeneous and GPU accelerated computing these days, from one generation to the next. For example, here is a very quick picture of, I'm just going to quickly touch on a couple applications to give you an idea of, again, these motivated cases at the top levels, the fastest machines in the world, because this is the technology and the approaches that filter down to us. Here's an example of climate modeling done at a 200-kilometer scale on the top here. And 200 kilometers, pixels, if you will, of weather, actually it's three-dimensional, so 200-kilometer boxes, if you will, of weather is an enormous, they're not actually 200-kilometer high boxes, but well, without going into technical details that we don't care about here, the pixels that make up the weather here are enormous. 200 kilometers, if you look out your window, you can't even see 200 kilometers in each direction, and that's what we're smearing everything out to in order to accommodate a model back around 2000 and, I don't know, I want to say 6 or 7 time frame. I think there's a timestamp on this actually. The current versions of this run at something better than 25 kilometers. This is actually a little bit obsolete here on the bottom. You can see a lot more scale and detail starts to show up, a lot more science and realism starts to show up when we can decrease the mesh size, get a smaller pixel size. Even a 25-kilometer pixel is huge, but when you stick your head out the window now, you can at least probably see 25 kilometers, possibly see 25 kilometers in each direction on a clear day. So you get some idea of the enormity of the problems that drive things on the top scale. These are the things and the technologies that we get to leverage down at the desktop level, although some of you there today may have grand challenge problems like this that are at this scale. Another example, one that's a little bit more accessible in terms of its human scale, is combustion simulations, where we might be modeling combustion in a piston or in a turbine generator. However, they turn out to be equally challenging because the pixel sizes that you want there are no longer kilometers. Now they're micrometers. Chemistry happens on a very small scale. So you want to be able to model things on a very, very small scale and at the same time be able to accommodate the fact that chemistry, a lot of interesting chemistry is happening, species of chemicals are changing from one to another, thermodynamics is very challenging, and most importantly, it's all turbulent. This is very nonlinear kind of behavior that means you can't have a small enough mesh to accommodate it. So it's a very important problem as well. It's obviously important, but so is making cars run more efficiently and pollute less, making electricity generation turbines that you run, making them 1% more efficient has ridiculous economic consequences. So these kind of simulations are run at the very largest level. Another one, just to give you one that's completely different direction, is brain simulation. These days, the brain projects that are happening in Europe and the United States are look great interest because we're at the point now where our machines are large enough that we can actually begin to approximate simulating real brains of interest. As a matter of fact, we're somewhere in this gap right here between monkey and human brains in terms of how many synapses and neurons we can simulate. So these are the kind of problems that drive the technology to give us OpenACC. That's the community it comes from, as well as MPI and some other things we'll talk about. So that's the motivators. Those are the drivers, and those are the places where you can look if you want to see if what you're learning today is actually really relevant. Is it going to stay relevant in 10 years? These people are using those technologies right now. They're the, as I'll talk about, they are the only ways to achieve scalability and get performance on these big supercomputers. So you don't have to worry that what you're doing, what you're learning today is faddish or trendy and is going to be supplanted by something else. Instead, these are the anchors for doing computing at large scale. So why is parallel computing necessary at all? Why are we going, the things we're going to learn today involve thinking in parallel. This is slightly less convenient than us just writing serial code and just saying run on a faster machine. Why aren't supercomputers just really fast machines at running your serial code? And indeed, that was what supercomputers were for a good part of their early development, just a machine that would take your serial code and run it 100 times faster than your desktop machine. So why isn't that the case anymore? Why are these large parallel machines different types of beasts that are made up of thousands or tens of thousands, or these days millions of nodes? And the answer is, well, I won't give you the answer, but I'll give you the proof that that is the case. The proof that that is the case, that serial computing is kind of dead in terms of getting high performance, in terms of being anything that's able to effectively use hardware, even the hardware in something like your desktop machine. The proof that this is dead can be seen in benchmarks, like in this case here we've got SpecIt, which is a benchmark. There are lots of benchmarks out there. Pick your favorite. They'll all show the same behavior, that over the years, over the decades, and we can run this graph all the way back to the 50s, over the decades, computers got faster and faster at running your serial code. Sometime around the year 2004, and we'll see a few more graphs like this, we'll see the consequences of this, somewhere around the year 2004, serial computing kind of plateaued and ceased to get faster from year to year to any significant degree, at least nowhere near the extent that it was previously. Serial computing for the past decade plus has been stuck at roughly the same levels of performance. You can see this most obviously if you look at the clock speeds of the computers that you buy today. They're a couple gigahertz plus or minus. If you go and buy a PC or a high-end workstation, if you build your own or if you buy a laptop, these days your clock speed, the speed with which that processor runs, is going to be, again, a couple gigahertz plus or minus. If it's some power-conserving device, it might run close to gigahertz. If it's some fast high-end workstation, it's somewhere over 3 gigahertz. But at any rate, it's a couple gigahertz. That wasn't true for decades here. It was always the case that clock speeds doubled every couple of years. Every 18 months or so, as a matter of fact, clock speeds doubled. So what has happened that's caused this plateau? How does this involve you as programmers? How is this related to OpenACC? Well, to start to answer that question, it's not that Moore's law is dead. Moore's law, which is this commonly referred to, I'm sure all of you at least heard the phrase, the buzzword, many of you have probably heard it misapplied to other areas of technology. Moore's law is an observation that Gordon Moore made back in the 60s that it looks like transistor densities, the number of transistors that we can cram onto integrated circuits, which at that point in time were very new. It was a new invention. Transistor densities were doubling about every 18 months or so. And he said, you know, well, I predict this is going to continue to happen for a while, that we're going to be able to cram twice as many transistors in any given area of our new integrated circuit or chip for a while. And amazingly, it has held true now for 40-some, 50-some years. That's remarkable given where they were starting and how many different revolutions in engineering we've gone through in order to maintain that. But Moore's law is not dead, not yet. It's getting very, very close to not being viable anymore. If we look at this slide from Intel, for example, we can see that we've continued all the way through the past couple of years here, and all the way through next year. We're continuing to crank out more and more transistors over an area at an incredible pace. So Moore's law isn't dead. So why did the performance of chips running serial code quit taking advantage of these hardware advances? And this is the reason. This is the reason for All of parallel computing, this is the most important thing in computing today in general, be it your cell phone, be it your laptop, or be it a supercomputer. It is quite simply heat. It is quite simply that dissipating heat, getting rid of heat is now the dominant issue in designing any computer in terms of performance. And to give you some perspective on how impressive it is that we've reached the level we are today, here is the watts per square centimeter dissipated by chips over the past couple of decades or more here. And chips today, computer chips today, chip on your laptop in front of you, certainly on your desktop today, they are running at close to 100 watts per square centimeter of heat that they're dissipating. And at first that might seem like a kind of an abstract number to you, but you certainly know what a 100-watt light bulb, the heat a 100-watt light bulb puts out. You would never put your hand on a 100-watt light bulb. You burn it instantly. That is the amount of heat that a modern microprocessor is dissipating when it's running, when it's actually doing some computing in a normal desktop machine today. That is an absurd amount of heat to try to dissipate without doing something really exotic like liquid cooling, which is indeed how supercomputers of the past operated. So we are really running chips today hotter than a hot plate. That's actually hotter than a hot plate. Hot plates don't do 100 watts per square centimeter. We're running computer chips today hotter than a hot plate. We're getting up close to very near the temperatures that we run nuclear reactors at. However, you'll notice that this graph has kind of plateaued as well, right around the year 2004, 2005. In other words, what happened around 2004, 2005 is that we weren't able to keep cranking up the clock speed every year because the chips would start to melt. And so indeed, here's the clock speeds. As I mentioned, your clock speed is probably the crudest way for you to understand how fast your serial code is going to run. Your Python script or your 40-year-old Fortran code, how fast is it going to run just in serial mode? Clock speed is a fair indicator of what kind of improvements you're getting. And again, clock speeds plateaued right around 2004. Around the same time, the temperatures hit this peak, around 100 watts per square centimeter. So it actually turns out that the reason that we are all here today being parallel programmers is because we don't have the alternative of being serial programmers and just hoping that our computers will run our serial code faster, because the chips will melt if we run them any faster. Liquid cooling, or doing something exotic to deal with the heat problem, is an option, and in the past it was indeed the way that supercomputers were constructed. Here's a picture of a Cray from the 80s. This thing in the foreground right here is the cooling tower. And there was floor inert that bubbled through. This looked like a fountain when the thing ran, and that was what was used to cool the machine. Well, cooling supercomputers is barely viable. As a matter of fact, it's not really even an attractive option today. People don't like to do liquid cooling if they can avoid it, and most of your really huge machines today are instead air-cooled with extremely serious air cooling setups, but still air-cooled. On the other hand, liquid cooling your desktop or your laptop or your cell phone is not an option. And so instead, parallel computing became the end run around the laws of physics here. So if we can't keep cranking up the clock speed, but we've got these more transistors to work with every year because Moore's law didn't end, we kept getting more and more transistors every year. What if instead of having one core, what if instead one processor, what if instead we went to a couple of processors and we'll figure out how to parallel program them later, but we'll at least have twice as much computing power at the same clock speed. And indeed, that's the math that started parallel computing. So right around that time is when the transition happened on the desktop in the whole world, everywhere. It's when people started to say, hey, if we're going to make cell phones, we better have 2 or 3 cores in them. So today, your cell phone has multiple cores in it in response to this issue. And the math that was done was basically looked kind of like this. Here's a orders of magnitude kind of math here. If we have a single core and it has whatever area and we're running it at whatever voltage, probably 5 volts, and we're running it at a gigahertz, and it takes 100 watts to run, and we get however many flops of performance out of it. What if we instead had 2 cores, but in order not to have the heat dissipation, because we've got 2 cores now, we've got to cool them both, what if to keep the heat dissipation the same, what if we reduce the voltage by a little bit, 15%, reduce the clock rate by a little bit, then we're going to have the same amount of power because of the way power scales. But we're going to have about 1.8 times the performance we used to have. This math right here is exactly what drives parallel computing. It drives all computer design today because everything today has multiple cores in it. Your Xbox or your PlayStation has multiple cores. They all have 3 cores in them. Your cell phone has multiple cores. If you look at how Apple and Samsung are battling it out right now, one of the specs that they'll talk about with each other is how many ARM cores they have in their phones to make things run smoothly. So everybody's gone to multiple cores, and this is the reason here, is that with multiple cores, you can throttle you back a little bit. You can keep the clock speed stuck at a couple gigahertz, but get more and more performance by adding more and more cores. That's parallel computing. This is the reason that we're all doing parallel computing. This is the reason that you can't avoid it if you want to make your video game run as fast as possible on an iPhone, if you want to make an Xbox game these days, or if you want to run your numerical climate modeling simulation on a supercomputer, parallel computing is a must. So, parallel computing itself is all about taking advantage of these multiple cores. So, it's understanding when things can be distributed in parallel and when they can't. The classic problem it goes all the way back to the Mythical Man Month, a book that Brooks wrote back in the early 70s, which captured a lot of things to drive parallel. If you're a software design aficionado, you've certainly read this book. It's a classic in the field. And Brooks observed that 1 woman can make a baby in 9 months. Does that mean that 9 women can make a baby in 1 month? No, that's absurd. On the other hand, 9 women can make 9 babies in 9 months. So you can do things in parallel effectively, but you have to know how you can do them in parallel. You can't just cram everything faster. You can't take any algorithm and just make it work automatically faster on multiple cores. You have to instead understand when you can and when you can't, and how you can do things in parallel. So let me give you, go back to a more scientific model here, which is a weather model. As I mentioned to you, weather modeling has been done really successfully over the past 3 or 4 decades. The weather models have gotten much, much better to the point where predictions today for important life-saving stuff like hurricanes and whatnot are much better than they used to be. That's because weather models today run on much more powerful parallel computing platforms than they did back in the 70s. But your weather model back in the 70s probably looked like this. It looked like you took a weather map, you broke it up into a grid, and you threw a CPU at it. Maybe a supercomputing CPU at the time, the fastest CPU that you could buy from Cray, basically, but you threw a CPU at it. And it went over this grid, and it did its map operations over the grid, and that gave you your next step in time. It did its operations about fluid flow, again, the wind direction, temperatures, pressures, humidities, and it did all its calculations on each element based on its neighbors, and then it went over the grid again and advanced forward in time 1 more minute, and then went over the grid again and advanced forward in time 1 more minute, and eventually you get your weather forecast a couple hours in the future. And that's how your classic serial weather model works. Well, instead, it would be nice if we could do this faster by doing it in parallel. And it so happens a guy named Richardson back in 1917 came up with a way to do weather modeling in parallel. And the year 1917 should certainly intrigue you because this predates any kind of digital computing and any kind of effective computing, mechanically computing. And so you might wonder, why is a guy in 1917 worried about doing things in parallel? Well, because he envisioned that if we had a bunch of meteorologists scattered about the land, that they might be able to do a more effective weather forecast if each one of them went and got on their telegraph and communicate with their neighbor and said, hey, what kind of weather do you have looking out your window right now? Because I'm going to put that in my weather model that in the future, coming from the west here, I could expect this kind of front. And I will tell you to the east that you can expect this kind of weather coming from me. And we can all do our calculation on paper, figure out what the weather's going to look like an hour from now. And once we've figured out what the weather looks like from an hour from now, let's call each other up again and say, hey, an hour from now, this is what you're going to be getting from me. And what am I going to be getting from you an hour from now? And so we could advance through time by just communicating with our nearest neighbors only. So if a neighbor was over here somewhere, you'd eventually find out what his weather was propagated through your communications here. But all you needed to do was get on the telegraph to your nearest neighbor, and you could exchange information, and you could compute the forecast into the future. Well, this is hopelessly naive, as it turns out, because weather modeling and fluid flow problems like this have this, again, this chaotic nonlinear nature to them. So today we realize that you need incredibly fine grids. They take ridiculous computing intensity. You're not going to do it with pen and paper. However, the algorithm itself is sound. So today, if we were to run this on a machine like the National Weather Service does, let's say that they had a machine with 4 cores. And indeed, this would be a workstation like they might very well have had in, I'll say 4 cores, actually would be like a 70s, 80s kind of technology, but it might be something you run on your laptop with 4 cores if you wanted to run a toy weather map, compare yourself to National Weather Service or whatnot. If we ran this with 4 cores on a computer, what they would do is the computer would take and break the weather map into 4 pieces. So this core here with the green area would only have to compute 1/4 of the map. And so it's running a code that looks very much like the serial code, but it only has to run on 1/4 as many elements. It only needs to do 1/4 as many calculations. As a consequence, we would expect that this would run about 4 times faster. And indeed, that would be the case. Now, the kind of programming technology we would use to program this would be OpenMP. OpenMP is the best way to program multiple cores, where you've got 4 processors working on the same weather map, the same memory. This is a shared memory machine, hence the title here. It's a computer where the whole problem fits into the same memory, and all the processors access that memory. So this is the equivalent of having 4 meteorologists in a room where they're all taking the map and dividing it up into quarters and saying, I'll work on this quarter of the map, you work on this quarter of the map. And then when necessary, when I need to know what's happening to the north of me, if I'm this quarter in the southwest, I need to know what's happening in the north, I turn to this person to the north and say, hey, what kind of weather are you generating? And then I can get the data that I need to worry about this border up here. So it's 4 meteorologists working cooperating in a room. Instead, what we're going to do with OpenACC is we've got to deal with the fact that our accelerator, our GPU, is actually a separate device in our computer that doesn't share memory. And we'll see as we go through today that this is the dominant issue in programming in OpenACC, is that our memory that's in our computing device, our GPU, is not the same memory that's in our CPU. And so we take our problem, which starts out in our CPU, it got loaded from disk and it got initialized and you've set in all the parameters and everything here. We have to take that problem and send it over the bus. And it turns out that this bus here is a bottleneck. The PCI bus that connects your accelerator and your CPU, you might think a PCI bus is pretty fast because it's fast enough for, you know, your video card if you're playing video games to get information back and forth. But compared to the speed between a CPU and its memory, it's pretty slow. So it takes a while to cram this over the bus into the GPU memory. Once it's in the GPU memory, you hope that it can be operated on very quickly. That's what we're going to try to do today. We're going to leverage the fact that GPUs have a lot of cores. GPUs have thousands of cores. The nodes that we're going to use today have thousands of cores in the GPU. So we hope that with thousands of cores marshaled together to work on the problem, it's going to be very fast and be able to solve this weather map very quickly. And indeed, that's the case. That's the way we would run a problem like this today. But when we're done here and we need to get the result back to communicate with the rest of the world for the processing, we have to cram it back over this bus. So we've got to slide the problem back and forth. It's not quite as simple as the old shared memory world where we're all sharing the weather map. Instead, this is like we've got one meteorologist here, and he's got this very bad connection to a room full of calculators, people that can calculate stuff, but they're not really, we're going to find out the cores in the GPU are not nearly as sophisticated as a traditional CPU core. So I call them here savants. So they're like a bunch of math savants. They can do one thing very well. They can do number crunching very well, but we need to get the information back to the CPU to do more general stuff on it. So we'll understand this model very well by the end of the day, and we'll have done some exercises and problems that look like this. Now, the last possible way of doing this, and it's a very important component of parallel computing, and it's the way that the Weather Service actually does a very large problem like this, is that they will, for the sake of being able to use a very, very huge machine, if you want to use a machine today that has hundreds of thousands or millions of cores, which is the size of the large supercomputers today, you instead have to break the problem up into a bunch of pieces. They can't all share the same pool of memory because physically sharing the same memory chips across a room-sized machine is impossible. Instead, you have to put the memory in a bunch of different boxes scattered around there. If you try to connect all the CPUs to one central pool of memory, they would all spend their time fighting over that memory. Memory contention is a big problem whenever you have a lot of cores and a single chunk of memory. They all spend their time fighting over basically the electrical connections to those chips. And so you spread the memory out so that you can build a very big machine. But once you've spread the memory out across the room, across a bunch of different blades and a bunch of different cabinets spread out across a physical room, and these big machines are the size of, you know, a football field, they're spread out across the room. Now you've got to communicate between these CPUs and their local memory in order to get the weather information that the other CPUs need to do their calculations. And so now you've broken the weather map up into a bunch of, in this case here, we've broken it up into 50 different states. There's a CPU for each state. So it's running that same type of code, but only on its state. So we hope that it runs about 50 times faster. But to communicate with the neighboring states, which you do need to do to know the weather that's propagating across the borders, you've now got to use the network. And on a supercomputer, that network might be some proprietary InfiniBand, or in Bridges, we've got Intel's OPA network. In a cluster that you build yourself at your university, it could be Ethernet, for example, but it's a network. You've got to communicate across the network. It's not as simple as just grabbing something out of memory anymore, anywhere on the weather map. If it's something that belongs to one of your neighbors, you've got to request it over the network. And the way you do that is using MPI. So those are the three different programming models, and the pieces actually do fit together in a way that makes sense. So this is the way modern programming looks, is that if you've got a single multi-core machine in front of you, and every machine is multi-core today, as I emphasized, your cell phone is multi-core. There's nothing that's not multi-core. The world of just serial single CPUs is dead. So if you've got a multi-core machine, so here's the memory and here's 6 cores. So we've got our 6-core chip in front of us on your laptop or on your workstation. So let's say you're in a department and you got a workstation. This is the machine you use. The way you program it is with OpenMP to use all of those cores at once. That's the way that you can take your serial code that runs on one core and is bottlenecked just by only going in a serial fashion through the code, and you want to make it run, say, roughly 6 times faster because you've got a 6-core machine available to you. You could use OpenMP. If you plug an accelerator into that machine, and you would like to use an accelerator to make everything run faster, then you use OpenACC, and that's what you're here today to learn, and that's what we will learn. So you'll walk out of here today knowing how to use a GPU, or there are other accelerators too we'll talk about, but most of you are probably thinking accelerator programming is NVIDIA GPUs. That's not unfair. That's the majority of the market at this point. You'll use OpenACC. So that is how you could plug into your workstation this magical device that all of a sudden runs your problem 50 times faster, everybody hopes, OpenACC. However, if that's not quite enough and you need to actually run 10,000 times faster or 100,000 times faster, then there's no alternative but to buy a whole lot more nodes. So now you're building yourself a cluster, or if you got a lot more money, you're building yourself a supercomputer like Bridges. And you buy a whole lot more of those nodes, you connect them together with the network, and then you use MPI to program things across that network. So those are the 3 pieces of programming that make up all of modern parallel programming. You're either programming for multiple cores on any given processor that you can buy today, or you're plugging an accelerator in and using it, and I should say because you can certainly combine these, and on the big machines you combine these techniques. That's what our summer boot camp is, as a matter of fact, is combining all 3 of these techniques together successfully, because that's the ultimate amount of flexibility to use the very largest machines. And lastly, if we've got a bunch of these nodes together in a room or theoretically spread out, there are distributed clusters out there, you can use MPI to communicate between them. To give you a reality check here, here are the top systems in the world. There's a list called top500.org. If you're interested in this kind of stuff, you can go there. It's a great site. It's well organized, so you can play with statistics and pull up different lists, rank different ways. If we look at the top 10 machines as they rank them based on a benchmark that's generally accepted by at this point in time as a way to rank machines, you'll see that the top 10 systems, this is June 16th list, it hasn't changed much since. They came out with, every 6 months they come out with one. The one in December is almost exactly the same. If we look at the list here, we will see that of the top 10 machines, almost all of them have some kind of accelerator or another, which is what you're learning how to program here today. So the very biggest, fastest machines have accelerators, although you might say, oh, the very fastest machine here, which is a very custom machine, it's a Chinese machine, it's very custom, doesn't have an accelerator, but guess what? The way that you program its hardware, it's built as a bunch of accelerators, basically. Its fundamental accelerator is OpenACC. So the fastest machine in the world right now, OpenACC is the way that you access all of its components. The other machines on the top of the list all have accelerators, which means you program them the same way. And there are a few exceptions here, though. For example, the IBM Blue Gene series does not have accelerators in it. However, that is also the end of the line for the Blue Gene series of computers. So the top 10 list and certainly the top 100 and top 500 computers over the past decade have been very, very much invaded by accelerators, GPUs mostly, NVIDIA GPUs, and that's what you're here to learn. So By the way, if you think that the power limitations, if you follow along with the stuff in pop science and everything, and you look at Exaflop computing, the newest machines will run at trillions of trillions, thousands of trillions of flops floating point operations per second. If you look at those machines, they talk about power and everything so much, as I've talked about power at melting your laptop, making your laptop warm in your lap, or your cell phone run warm when you use it. Power is an issue at the small scale. At the large scale, it's a problem too. Big machines run 20 to 30 megawatts of power. Ultimately, all of computing power, all the power you put into the computer turns into nothing more than heat. The output of computing, you and I think of it as information, a simulation answer. The physical reality is all of the output of computing is just heat. Well, that's the problem here. But at the very largest machines, I talk about 20 to 30 megawatts of power. That's the limiting factor on how big of a machine we can build today. Nobody's willing to build a machine that takes much more than 20 megawatts of power. It's possible. We could throw enough money at it if humankind's existence mattered. But basically, for practical purposes, that's the limitation. It's interesting that at 20 megawatts of power, we hope that the next generation of machines will be able to simulate the human brain. I showed you the human brain simulation is kind of one of the ultimate goals for the next generation of computers. And our brain takes 20 watts to run. So we are hoping with 20 megawatt machine, we can run simulation of a brain that takes about 20 watts to run. So it gives you some idea. There's a lot of improvements to be made in the world. So even though Moore's law is reaching its end, and there are lots of other technologies that are coming to a conclusion after decades of tremendous improvement, there's still a lot of room to go, lots of things to do. So I hope this has given you some perspective on things, because as we get into the technical material, which is immediately to come, I will continually refer back and say, okay, well, this is something you might do with MPI instead. This is something that doesn't apply here. I hope I've given you some perspective on the pieces that make up parallel computing, where they come from, and most importantly, this stuff is no fad. The laws of physics aren't going to change anytime soon. Parallel computing is not because computer scientists like parallel computing. They like concurrency. They like Haskell and fun languages like that. No, parallel computing is driven by the absolute laws of nature, which say if you crank up the serial speed anymore on modern processors, they'll just simply melt. So you need to have multiple processors to spread the work over, and that is where OpenACC comes in.